Well, hello there. It's Friday night again, and here we are together again. I can't think of a better way to spend my Friday nights. And today I have got something new that I'm going to add to the videos, and I'm pretty excited about it. So I'm going to show you right here. Okay. This is IOLab. It is a remote sensor and it can measure force. See, there's a rubber band here. And so when I hold it here, I can measure acceleration. Okay, let me show you how it works. This thing is really cool. So I'm going to move this sensor, and when I move this sensor, you're going to see what the data is here. Okay, so this is pretty cool. I think it's really awesome. The plan is that maybe not this year, but to do the labs online, we're going to use this sensor in the future. So this is the future, but it's pretty new and everybody is kind of afraid of it, at least normal physicists, but maybe I'm not normal. Okay, so it has different sensors. Internally, it has an accelerometer, meaning if I shake it, I can measure the acceleration that it's moving, and we have force. Okay, so I'm going to select the accelerometer and the force, and then I'm going to go validate your configuration. All right. So first thing we're going to do, okay. So up at the top here, we've got our acceleration, and then down at the bottom, we've got force. Okay. And so it can show us in real time what those values are. Okay. Now when I do this, okay, what's really interesting, okay, AY, I'm going to delete that, and AZ. Okay, only AY. So see right here, right? Um, this thing is measuring, and let me zoom in on here so you can see it. Okay. So this is the acceleration just right now, this thing's sitting here. And I've created a little stand here. Oh, hang it close to my face. Okay. Well, it's just hanging here right now. And when it's doing that, okay, I don't know why it doesn't want to put it in sync with me. But this thing is just measuring the acceleration. I'm going to hold it up. There we go. Okay. Oh, see, when I moved it, there was a bunch of acceleration. Okay. So I'm going to stop this thing here. But normally, you could see here that the acceleration acting on my sensor, it's right here around 9.81. And that's exactly what it should be. Okay, stand here. There we go. So I gotta hold my head here because my computer tracks me. Wow. All right. So my sensor's just hanging here and it's measuring the acceleration. Now this thing weighs 0.22 grams or kilograms. Okay, so 0.22 grams. I think it says the mass somewhere. Okay. And so here we get its mass in its weight in newtons is 3.07, and then right here we get acceleration due to gravity. Super awesome. Okay. So that's the acceleration. Now I can add some force to my sensor. Okay. So if I pull on this now, okay, then my force is going to go up. Okay. So here's my force. I'm going to pull on this now, and the force increases. Okay. So it goes up to 6. I can increase my rubber band. We're not supposed to go above 10. Okay. So I can stretch my rubber band here. Okay. And the rubber band is pulling down at a force of about 8 newtons. Okay. But when I do that, the acceleration goes away. Okay. So this thing is really cool. We're going to use it as we go through the lecture. All right. So that was our first set of data. I'm going to make a new set here. We're going to get that back. We will do force, and we'll do acceleration. All right, so I'm gonna get my sensor ready here. All right, let's continue with chapter 4. This is going to be a quick conceptual video, and then we are going to do some problems. Okay, so watch this video if you want to understand conceptually what's happening in chapter 4, and then we're going to do some problems from the homework. Okay, and then with chapter 5, I'll do a conceptual video about chapter 5, and then we'll do some homework problems. Okay, so we're going to go through the most important things from the chapter that you need to know for the exam. All right, the kinds of forces that we're going to be dealing with. Okay, first, an object's weight. Okay, that's just how much gravity is pulling down on our object. All right, so here is my object is right here. Some Pokemon jumped on it. Okay, I'm going to get rid of AX, just have my acceleration here, and then I am going to, on this one, yeah, it doesn't matter. Okay, so it says that the force that the sensor is experiencing right now is 3 newtons. Okay, let me zoom in here. All right, so 3.2 newtons. I added some Pokemon stickers. Okay, that's the weight. It always pulls down. That's all it does. Spring force, okay. A compressed spring exerts a force on an object, and a stretched spring exerts a force on an object too. Okay, let's look at our force diagram here. Okay, I've got my rubber band, and now I'm going to. Yeah, I've got my rubber band here. It acts like a spring, and I'm going to pull down on it. Okay. And as I'm pulling down on my spring, now I'm experiencing a force of 8 newtons. And when I let it go, hey, there's acceleration there. Okay. So when I release the spring, it goes back to its natural equilibrium. I can't push on this because it's not a rubber band. Okay, but that's okay. All right. We're going to stop that. So. That's my spring force. It could be a rubber band, or it could actually be a spring. Spring. Ah, yes. Here is my spring. Okay. This one is only stretches. It doesn't compress here. I can't really compress it, but I have another spring here. Okay. Where I could push on my spring. Yes. Okay, so I can compress my spring, or I could pull on this one if I wanted to. Okay, and this force is only related to how much it's moved from its equilibrium position. Okay, so that's the force of my spring. All right, a rope exerts a tension on my sled. Yes, it does. Okay, so here's my sled, and I'll run my accelerometer again. Okay. So we're going to do this experiment now. Okay. I'm going to pull on it this way. Yes. My force sensor goes up. Okay. And this is force in the Y direction. That's along the component of the thing. Okay, but watch what happens to my force here. Okay, so I'm going to keep this level, and then I'm going to go up here like this. See? My force goes back to 0. Okay, so I'm going to pull my force sensor. This is at a normal angle, and as I increase my angle here, it kind of drops, right? If I go over here, it's higher, but if I go here, now I'm only a component of it is in the Y direction or the X direction, right? If I hold it over here, it's higher. Okay, so now this is like we're doing We're doing trig of the angle, okay? See, if I go down here, this is the maximum. If I go up at an angle, then it's 0. If I'm perpendicular, okay, it's basically 0, okay? That is, yeah, it's not there. Okay. So 1 is basically 0, okay? Now here's my maximum force, okay? So, but that's, when I pull here, the only force acting on here is the tension in my rope or the rubber band. Imagine this is my sled. See? Now we have a sled and we can measure the force with a computer. You can actually rent one of these for 60 bucks. I should have had to rent one. They're really cool. All right, let's move on here. Moving on. Yes, we are moving on. All right. Tension of force in the rope. Okay, friction. The force exerted on an object that is present against the surface is in a direction perpendicular to the surface. Right? That's true. Friction is always perpendicular to the surface. Right? Let's do some friction here. Right? All right. Let's switch over now to uh, the experimental webcam. Okay. And okay, so here's my sensor data. And as I pull this along now, okay, let's zoom in on that. Yes, we'll get some frictional data here. We can actually get friction due to data, okay? So here's my thing, okay? It's 0 spot is at 1.4, but when I pull here, see, I've got some frictional force there. My force due to friction is non-zero, okay? Ooh, wow, I can do static friction, okay? I'm gonna zoom in on this guy. Oh my gosh, this is amazing. I can actually measure friction instead of using your mind, which is cool. You should always use your mind. Okay, as I pull on this, see that my friction goes, the force of my friction goes up. Right? To get that to move, I had to. Now I got wheels on this side. Okay, so I'm gonna now the force to get that thing to move is basically 0. Right? There's no force here. Right? To keep it moving. Wow. Okay, but if I turn it over now to get this to move, I need to apply a constant friction, right? There's a constant force. So I'm having to exert 2 newtons to get this thing to work. Okay, so this is my force due to friction. Okay, and now what if I add something heavy? Oh yeah, let's start putting some books on this. Well, I can't. It's wheels are on that side. Oh shoot. Ah, shoot. Well, let's put this. Oh, this is a heavy prism here. How do we get this thing on here? Oh, perfect. All right, we added some. What do we add here? All right, yeah, we added this thing here. Okay, here's our. Okay, now I'm gonna pull on this guy. What happened to the our sensor? Okay, here we go. Target duration timed out. Oh shoot! Delete the page. Okay. All right, we're gonna start this bad boy up. Actually, you know what? We're just gonna do a new page here, and we're only gonna do force because I don't care about the acceleration right now. Okay, I'm gonna start my force sensor here. Okay, we got some force. Sweet. Measuring the force. It's basically 0 right now. Okay. Now to get this thing to move, okay, takes about 3 newtons. See that? I made the normal force heavier. Right? This is much heavier now. So to get this to move, I got to get it up to about 3 newtons. Okay, that's the force of friction to keep that thing moving. I'm going to take this heavy prism off. This thing is pretty heavy. Okay, now to get this to move, it only takes 2 newtons. Okay, I changed the normal force on my sensor, and now I need less force to get it moving. Okay, that's the force of friction. Okay, and I can put different surfaces on here. Okay, let's do it on metal. Right, that has a different friction than paper. What do we got here? Uh, is that different? We're gonna have to zoom in. Okay, on metal. Oh, but there's magnets there. Shoot! Those things are magnetic. Mm. Mm. Oh, I got plastic. Let's try it on plastic. Okay. To get it moving on plastic, it's about 1.9 newtons. Okay. That's some pretty good friction. Try it on paper. A little bit higher on paper, maybe. But it's about the same, honestly. It's not really. Well, anyways, but when we change the normal force on this, it's definitely, if I make this heavier, here we go. There it is with, yeah, with heavier normal force. Now let's watch something else here, okay? When I first start pulling on this, before it starts to move, I'm going to keep increasing my force here, okay? And, oh, did you see that? Oh, shoot. That was perfect. Well, this thing is amazing. Now, before this thing starts to move here, let's see what force we can get it to. Okay, 3.2. Aha! See, now it's sliding, and look at that. Oh my gosh, this is so amazing. I think I think I'm gonna cry. You can actually show this and go, oh my gosh. Okay. See that? The force of static friction is higher than kinetic friction. Okay, so it's not sliding now. Oh, see, once it starts sliding, the friction drops down. Oh my goodness. We're gonna stop this and look at this. Look at this. Look at this data. Look at this data right here. Gosh. Oh. All right. So this is kind of amazing right here. Okay. So see what happens is in the first part here, right when this is about to start slipping, okay, we have to get up to about 3.5 newtons. And then as soon as it starts to slip, the friction goes down. Okay. So static friction is higher than kinetic friction. That is totally amazing. Okay. I'm going to say that again, guys. Static friction is higher than kinetic friction. So if you are in a car, you definitely do not want your wheels to start slipping because once your wheels start to slip and you're sliding, friction is lower. And so you do not have as much traction. That is the worst possible case scenario. So we did a little experiment here and we saw the difference between static and kinetic friction. Those two things are different. That is really, really important. Thank you, Sensor. I'm so happy I can do experiments on video now. All right. So that frictional force is caused by the the first few layers of atoms on the surface. Okay, it really is. Um, yeah, it's just caused by the first the few layers of atoms right on the surface. So whatever's going on here, the surface of these Pokemon, that's causing my friction. So molecularly, as those atoms are rubbing against the atoms on the paper, that's what's creating my friction. Oh man, I'm so happy I can measure that. Okay, the normal force is responsible for the solidness of the solid. Okay. The symbol for normal force is little n. Okay. Here's my sensor. Okay. Basically my hand is pushing up on this. Okay. And that is causing the normal force. Right. So it's my hand pushing up on this and the sensor pushes back down on my hand. Okay. And, in there, little n, that's the normal force. It's always perpendicular to a surface. Okay. Friction, like the normal force, is exerted by a surface, and it's always parallel to the surface. Okay, friction always never comes out of the plane of the surface. Okay, we have two kinds of friction. There's the friction when things are sliding. That's called kinetic friction because it's moving. Then there's the friction before it starts to move, which is static friction. Okay, and we saw that static friction is higher. We can see right here on the screen. We just did this experiment. Right here, static friction is a little bit higher, hey, maybe zero point 0.5 newtons higher than the kinetic friction. Over here, this is kinetic friction when I was sliding the sensor along the table. Okay. An object stuck on a surface and prevents its motion relative to the surface. Static friction points in the direction necessary to prevent motion. So friction always opposes your motion. If you're moving this way, friction is going the other direction. Yes. Yes, that is true. Moving on. All right. So a sled is moving to the right, but it's slowing down. Friction is opposing that. The woman is pulling to the left, but the crate doesn't move. That's static friction. If it's really heavy, it's going to be a lot of static friction. Okay. Uh, but it's always in the direction that would prevent motion, that opposes the motion. Drag. We haven't talked about drag yet. Drag is wind resistance. So as air passes over you, it slows you down when you drive your car. The force of drag causes your car to slow down. That's one of the things where if you take your foot off the gas, eventually your car will come to a stop. Um, for all intents and purposes, in most of these problems, we don't need to worry about drag. But if you have a leaf falling out of a tree, it's obviously very important. Um, let's do another experiment. Okay, I've got a tissue paper here. Okay, and if I drop this tissue paper, okay, put it over here. Okay, it's oh shoot, that wasn't very not a good tissue paper. Okay, so that falls pretty slow. But if I wad it up, falls much faster, right? There's no drag if you wad it up because you you decrease the yeah, you decrease the area, okay? Drag is very important for squirrels. Okay, they evolved to be fluffy so that when they fall out of a tree, they don't land as hard. Okay, so the drag slows them down and they don't land as hard, and so they live basically. Okay, um, grass does a lot to slow down the squirrel's fall too. Usually, if they land in tall grass, that grass is actually pretty squishy. It provides a nice cushion so the squirrel can live even if it falls out of a tree. Thrust is the force that occurs when a jet or rocket engine expels gas molecules at high speed. So the out of the back here, they combine oxygen and hydrogen. It basically creates water. Okay, but if you do it very quickly, you have large amounts of hydrogen gas and oxygen, and you mix them together and create a spark, there's going to be a massive explosion. Okay. And a lot of the thrust comes from hydrogen and oxygen. You create a spark and you get this massive explosion and it creates a bunch of water. Electric and magnetic forces. Okay. Yes, we have an example of those where Pikachu. Where would we be without my magnets? Yes. Obviously, Charizard is one of the most rarest Pokemon. Yes, look at that. Charizard sticks to the bottom. There's a force holding him here. Watch this force. Ooh, we get Charizard to stick. Ooh. Yeah, he did it. Ha ha. He's stuck on the surface. Ha ha. Amazing. Electricity. This is the electromagnetic force right here. That's why Charizard sticks to the surface. Moving on. All right. There's also forces inside of the nucleus of the atom. I mentioned that the atom was 99.9% empty space. However, it's actually even more empty because, yes, there are protons and neutrons, but guess what? Those are made out of other smaller things that are take up even less space. And so even the protons and the neutrons really, there's nothing there except these things called quarks, up quarks and down quarks, okay? They are also leptons, like electrons is a type of subatomic particle, okay? They quarks may have some radius, very small. Electrons have zero radius. They're really actually points as far as we can tell. Okay. Which means their density is infinite. So is each electron a little black hole? Maybe. That's fine. You're probably not going to get sucked into an electron. So actually, even in the protons and neutrons, there's nothing there. So when I'm sitting here, I knock on the table. What did I knock on? Nothing. It's mostly empty space. There's no table here. In fact, I'm not even sitting here. I mean, I think I'm sitting here. That counts for something, but I don't know. I know that there's really nothing around me. Everything I see is just photons bouncing off of energy fields between atoms. Okay, but there's nothing solid there. I don't know if I'm looking at a computer right now. Hopefully it's real. I mean, I've never actually seen you in a computer screen. I don't know. A ball rolls down an incline and off the horizontal ramp, ignoring air resistance. Yes, because we said basically air resistance doesn't matter unless we say it does, and then you have to, use drag. What force or forces act on the ball as it moves through the air just after leaving the horizontal ramp? Now, when I first looked at this problem, I didn't read the part where it said leaving the horizontal ramp. That means it launches off the end. Whoosh. It's flying through the air, just like a Pokeball headed for a Snorlax. Okay? As the Pokeball launches off the end, the Snorlax is sitting at the bottom. Is it going to catch it? Maybe. What are the forces acting on the Pokeball, assuming physics is real in that universe, which is really highly questionable? There's obviously no conservation of energy, which is why we don't actually have Pokemon. I mean, really, the only thing preventing Pikachu from being real is conservation of energy. Okay. Also prevents superheroes and zombies. Okay. If I'm just gonna throw this out there, but if we had a zombie apocalypse right now, it would solve all of our energy problems. Best thing that ever happened to humanity. We don't need oil anymore. We just put zombies on treadmills. We show them pictures of brains and they just walk towards the brains. I mean, they don't need to eat, really, right? They just walk around for years. So put them on a treadmill, make electricity. I mean, they don't eat. It's free energy, right? We can do that. I don't know. We'll have to wait and see when we start talking about conservation of energy. Okay, but the ball flies off the end. It's not touching the horizontal ramp. What forces are acting on it? Hmm. Okay. Well, the weight of the ball acting vertically down. Okay. Well, yeah, I think if it's in the air, if it's flying through the air, only gravity is pulling it down. A horizontal force that maintains the motion. No, things once they start moving, they just keep moving. You don't need a force to keep pushing it, right? Once it's flying through the air, it just goes. Can't be B. The force whose direction changes as the direction of motion changes. A force whose direction no, there's no changing force. It's just flying through the air. I don't even know what that's really confusing. The weight of the ball and a horizontal force. What is that horizontal force? I don't know. It's not a thing. The weight of the ball and the force of the direction of motion. There's no force in the direction of motion. Okay, it has to be a. That's it. So we need to isolate the ball. Okay. Think about what is acting on the ball. Usually there has to be something touching the ball. Okay, so that's what we're going to do. We're going to draw pictures. We're going to think about what is acting on this thing, and then we're going to draw force diagrams. All right, a steel beam hangs from a cable as a crane lifts the beam. What force acts on the beam? Well, there's the tension from the cable and gravity's pulling it down. Those two, if it's moving at a constant velocity, which usually I think a crane does, you don't want things like flying, whipping around. So, gravity and the tension in the cable. Okay, gravity and the force of motion. If it's moving at a constant velocity, this is really important. Okay, the net force is zero. Hey, let's do a little. Let's do another demonstration because I have this thing and it's really cool. All right. So we're gonna show this part here. Okay. I'm going to make a new page here. I guess I have to make a lot of pages. I don't know why I can't just reset it, but whatever. It's fine. Okay. So I'm gonna start running this. Okay. I got my force here. Now I am okay, and this is actually the force is in newtons, and I should reverse this. Okay, so I'm gonna say reverse my axis, man. There we go. All right. So the force here is acting downwards. Okay. The force of gravity is pulling it down is negative 3.2. Okay, as I lower this at a constant velocity, okay, it really doesn't change if I'm moving at a constant velocity. If I drop it, see, I'm like, whew, whew, then it changes. But watch, I'm gonna lower it slowly. Constant velocity. Yes. I'm still lowering it. I hit the table. Boom. Oh, see, now it's resting on the table. I'm going to lift it up at a constant velocity. Force doesn't change because it's in uh uniform motion. See, if I change direction, like then it changes. But if it's just moving at a constant velocity, no change. Okay. There's no force acting on it except the force of gravity pulling it down, tension pulling it up. The net forces are equal to zero. All right, moving on. So what's acting on the cable are the steel beam, gravity, and the tension of the cable. All right. A bobsledder pushes her sled across the horizontal snow to get it going and then jumps in. After she jumps in, the sled gradually slows it to a halt. What force acts on the sled after she jumps in? Wait, what? They said something about slowing down. Ah, okay. After she jumps in, the sled gradually slows to a halt. But um okay. Why don't they go faster? I'm so confused. Okay. What forces act on the sled just after she jumps in? Um, okay, so she's not pushing anymore. Okay, she jumps in the sled. What force is acting on her? Okay, well, gravity. Yes, gravity is pulling her downward. Yes, there's a normal force, right? If you're sitting on something, whatever you're sitting on is pushing up on you. Okay, well, I guess is she? Yeah, she's pushing. Yeah, we're talking about her. What forces act on the sled just after she jumps in? Okay, so we're gonna say definitely friction because it's moving. Gravity. Okay, so gravity, a normal force and kinetic friction. Let's try D. Yep. All right, we did it. And the force of the push. Well, after she jumps in, there's no more force from her push. All right, we're gonna identify forces. Okay, because in a lot of problems are like, what forces are acting on this? Okay, we're gonna learn how to identify the forces. What's a real force and what's a fake force? Okay. A typical physics problem describes an object as being pushed or pulled in various directions. Yes, we love things on an inclined plane and weird angles. That makes it even more fun. First, you must identify all the forces acting on the object. Some forces are given while others are implied. Yes, be sure to avoid including forces that do not exist. Yes, don't make up forces that are not there. Let's look at the guy here. He's going up the hill. Tension is pulling him up. They're pulling him the rope. Okay. That's one force. Gravity is pulling him downwards, and the normal force is pushing against his feet. Okay. Maybe wind resistance, but it's very small. Okay. What is the object that you care about? Identify it. Draw a picture of the situation. Always draw a picture. Draw a closed curve around the object. Okay, so draw a circle around it. Locate every point on the boundary of this curve where other objects touch the object of interest. Okay. Name and label each contact force acting on the object, and name and label each long range force acting on the object. Okay. Well, let's do an example. Okay. Let's go back to the thing here. Okay, we got I love the thing. Okay. We're gonna make a force diagram. We're gonna think about all the forces acting on this thing. Right? And we know what? We're gonna put it at a little incline here. Yeah, we're gonna put it. Hey, so we're gonna make it go. That's rapidly filling the gap. Okay. So many physics, so much physics here. Haha. It's a good thing. If I can choose the way that I die, I think it is doing a really cool thing. I mean, if you have to go, you gotta go somehow. All right. Oh, shoot. Okay. That one's a little too steep. Okay, so we got our thing here. Okay, it's on an inclined plane. Got a little sensor here. Okay, so let's identify all of. Oh shoot! I bumped it. Okay, that wasn't supposed to happen. Okay, so I'm basically right at the angle here when this thing starts to move. Okay, if I tilt this up just a little bit. Okay, too high. Okay, so right now we got the friction of this thing touching. Oh, see, we're right at this critical angle right here. Okay, so yeah, that is my angle. Okay, and let's actually turn it over. So I'm gonna put the wheels here. So I got these wheels. Okay, and then let's put it at an angle. Okay, and you can see the angle here with the horizontal. This angle actually probably is about right. Okay, let's start our sensor here. Oh, I gotta turn it back on. All right, there's my sensor. Right, and go. Okay. So my sensor is at -2. Okay, and this is really interesting because if I tilt this thing here, right, if I decrease the slope, it really changes my force a lot. Okay. So that increases angle here, right? I'm at an angle here. And if I go all the way to vertical, okay, where this thing is just hanging, right? This is about 3.2. Okay, and we can see now that when I put it on the ramp, it definitely changes the force that is acting on this thing. Okay, so we can see the trigonometry. That's amazing. See, you thought the trig was just a bunch of weird numbers, but no, I can see the trig. See, as I adjust the angle here, as I go steeper and steeper, right? It changes the force acting on the sensor here. See, I'm holding the rubber band here with my hand. So I'm measuring the force as I decrease my angle here, changes it a lot. Okay, so I'm gonna attach this up here somehow. I will put a something here to secure this end. Okay, there we go. There I got my pin there. Okay, and now I can pull my sensor here, right, and it will oscillate back and forth on here. All right, perfect. All right, so this particular angle, you know, I am holding my sensor. It's on the slope here. Okay. And I'm going to identify all of my forces. All right, now we're going to draw a diagram. All right, I'm going to turn the sensor off. That is fine. All right. Got our sensor there. We took our data, right? Because I love taking data. Okay, now we're gonna draw our diagram here. We are going to make a force diagram of this of what we just measured, because now we can actually measure force on the inclined plane. Man, that is the most exciting thing that happened today. Well, maybe the second. Tell you what the first thing was later. It's pretty amazing. All right, well, I'm going to draw my little sensor cart here. Okay, it's got some wheels on the bottom. Okay, so that basically it's pretty close to friction. Okay, and my sensor is on this ramp here. Okay, and there is a rope going up here, and it's tied up here at the end. Okay, so let's identify all of the forces acting on my sensor. Okay, that's what we're gonna do. We're gonna follow their little step there. Okay. So what do we do? Well, we're gonna draw a jelly bean around it. Yes. And anything that comes inside of the jelly bean, we're gonna make a force. We're gonna make a force diagram. Okay. So first of all, we have the tension in the rope here. Okay, tension is holding it up here. Okay, we got tension. Then we also have gravity here. Gravity is pulling our thing down here. This is M times G. Okay, that's the force of gravity acting on this. What else is acting on it? Well, okay, we have our normal force here. We call this little n in the book. Okay, this is our weight. That is our weight down there. Like and
Thank you, like and subscribe down below.
thanks.